So good afternoon, everyone, and thank you for ZESTAs for inviting me. It's a pleasure to be here and meet everyone and hear all your interesting ideas. My name's Angus Gray-Stevens, and I'm a CFD engineer at Cape Horn Engineering, and I'm going to be talking to you today about how we can use CFD that's been refined in ocean racing to optimize energy efficiency early in the design process. So I'm going to start by giving you a quick overview of Cape Horn Engineering's background to give the rest of this presentation some context. So we're a UK-based company that provides CFD consultancy services to the marine sector. The managing director is Dr. Rodrigo Azuta, and he undertook some of the pioneering research into the computation of free surface turbulent flows around ships in the early 2000s. Since then, we've been the core of the simulation-based America's Cup and Volvo Ocean Race design campaigns over the past 15 years. And in that, we've always been pushing the boundaries and developing new technologies, and we've helped 3 teams win the global circumnavigation of the world. So we've spent years developing and refining these tools in the performance-driven environment, and since then we've shifted our focus to the wider marine sector. And from this, we've got really first-hand experience of how powerful these tools are and how they have an important role to play in the route to true zero. So from our experience, we can see a large disparity between the use of CFD in performance sailing and the wider marine sector. And this makes for quite a good case study as to the potential of CFD technology when it's embraced early in the design process. The last America's Cup, which you can see a picture of on this slide, built the most technically advanced sailing yachts ever created. They were 72 feet long, fully foiling, and capable of 50 knots. And in the design of these, experimental testing was explicitly banned in the rules. So the 4 teams had to rely on CFD as their only design tool. The amount of development in this was enormous, and they went from a concept to refined racing machines in a couple of years. And that was using a design methodology that was centered around CFD as its core. The tools, workflows, and expertise that were developed in this are equally applicable to the commercial sector. And in reality, there's no difference between optimizing a vessel to win a race or optimizing a vessel to make it as energy efficient as possible. So CFD can be used to enhance the energy efficiency of ships through 3 primary mechanisms. The first is that it facilitates design exploration and optimization in a manner that's only possible in the simulation-driven approach. The second is that it speeds up the investigation of novel ideas and technologies, meaning that new solutions can be developed, explored, and implemented in a far shorter time frame. And the third is a sort of bigger picture outlook, and it's that the adoption of CFD in a simulation design approach facilitates a move towards a more holistic, integrated design process. So CFD can be used for design exploration and optimization to enhance efficiency. Large parts of the workflow using CFD can be automated, and this reduces the analysis time significantly. At Cape Horn, we can run around 50 cam water simulations per day, so we can explore a huge number of different vessels and different options. When coupled with the fact that CFD allows for rapid geometry changes, it means that a large number of designs can be evaluated in a really short time frame, and you can work out what solutions work and what don't. At its lowest level, this makes it really fast to compare multiple prospective designs. And then in that, you can focus on a single element of design. So for instance, a bulbous bow. You can find out the efficiency gain of adding a bulbous bow or the differences between different bow forms. At its highest level, this allows fully automated optimization programs to take place. So the simulations can be paired with an optimization algorithm and a fully parametric model, and then it can be let loose and it'll in an automated loop, and it'll effectively explore the entire design space. So the potential offered by this is huge. And especially in the context of the current world where there's an exponential growth of computing power, and it's becoming more and more available. The second means through which CFD can be used to enhance energy efficiency is that it allows the investigation and development of novel technologies. CFD removes the constraints of traditional model testing, and the need to sort of develop elaborate test rigs are removed. You can simulate in full scale, so you no longer have any complex scaling issues. The post-processing capabilities of CFD are immense, and I've been involved in both CFD studies and tank testing campaigns. And the level of information you can derive from a CFD simulation is like incomparable. Forces can be decomposed into shear and pressure components, and can be quantified for different surfaces. Pressure fields can be plotted, and streamlines can be used to visualize the flow, allowing a far more detailed understanding of what's actually happening to be developed. And this all comes together and forms an environment in which new technologies and new ideas can be tested and examined, and a very thorough understanding of what's actually happening can be developed quickly. This video was for the Windship project, and in that we explored the rigid wings on a vessel as an energy-saving device. As part of that, there was over 1,000 simulations that were run, and it resulted in a 2-digit performance improvement in a relatively short period of time. And that sort of shows how rapidly you can develop a novel technology. The final way in which CFD can be used to enhance energy efficiency is a more big picture concept. So that's rather than a direct application of CFD itself. Ship design traditionally follows a design spiral approach, which is functional and logical, yet at times it can be restrictive and inefficient. It's made up of several steps involving different teams, different data sets, and different tools. New tools such as CFD, FEA, and 1D system simulation software can be incorporated into it, and it leads to improvements. But the real advantage of these tools is that they facilitate a move to a more integrated digital approach. Moving all the design processes into a single centralized environment increases the project's efficiency, and the collaboration between the different teams is facilitated. And the digital twin methodology can enhance a vessel's energy efficiency by allowing multi-domain design space, and it lets every single aspect of the vessel to be tested and examined and optimized. So from a final slide, I just wanted to summarize how it's an important, CFD is important in the path to true zero. And it's a tool that the shipping industry has been relatively slow to adopt, but from our experience in performance sailing, it's got massive potential to enhance efficiencies. And the drive to true zero could really be the push that's needed for the full adoption of this. From this conference and from general knowledge, there's a huge amount of great ideas that are being developed for energy-saving devices, new fuels, and a number of ways in which emissions are going to be reduced. But I think it's quite clear that there's no single solution to all this, and it's going to be a number of different things that have to come together in a really complex solution. And in this solution, it's made easier if the hull and if all of the energy-saving devices are as efficient as possible, and that's the real power of where CFD can help with this. So thank you very much for your attention. I hope you all found that interesting and informative.
Thanks very much, Angus.